Good afternoon, everyone, and welcome to my thesis presentations. So first, thank you all for being here today. And in this talk, I would like to present my thesis about crop yield simulation using statistical and machine learning model. So the work has been supervised by Dr. Philip Arret from Paris Observatory, and we are in collaboration with Dr. Eric Ran from CIAT. So before going into any detail, I would like to put you in the picture of agriculture and climate change impacts. So as we all know, agriculture is vital because this is the basic material production of society. Also, it is an important economic sector. For instance, it can account for more than 25% of GDP in developing countries. However, there's many changes and challenges are now influencing the agriculture system. So the world population just reached 8 million last month, and it is expected to be 10 billion by 2050, meaning that the agricultural demand increased by 50% compared to the 2013. And conflicts, crisis, natural disaster, and change in climate will increase in frequency and intensity. So therefore, having the tools to monitor, estimate, and predict agriculture is very important. And when it comes to climate change, agriculture is among the most vulnerable sectors. And the impact of climate change on our agriculture are unevenly distributed among regions, depending on crops, projects, and scenarios. So for instance, here is an example from IPCC report suggests that the mean effect per decade can be -0.7 for rice, but it can be up to -3.3% for soybeans. And here are some more examples about a synthesis of observed impact on crop yield and productivities over different regions in the world for major crop species and different crop categories. So for instance, here, if we look at the Northern Africa areas, we see that maize and rice will suffer negative impacts and wheat will be positively affected. But a mixed effect can be found for soybeans. However, overall, we see that negative impacts are expected than positives. So we see that agriculture is important and the impact of climate change is negatively on agriculture. And this context leads us to our study on crop yield simulation using statistical and machine learning models. So during the thesis, several crops has been investigated, but in this presentation, I will focus on the two main coffee species, which are Arabica and Robusta, and they account for 60% and 40% of global coffee productions. And we choose coffee for several reasons. The first and a very important one is that more than 2 billion cups of coffee are consumed every day since 2002. And secondly, coffee is a major cash crop and important foreign exchange. So here is a map showing top coffee consuming countries and top coffee producing countries. So 90% of coffee production take place in developing countries, including those in Latin America, South and Southeast Asia, and Africa. And note that Brazil and Vietnam are the two leading coffee producers in the world, which account for about 50% of total global productions. And moreover, coffee has been proved to be highly sensitive to the weather and climate. So for instance, here a study showed that with 1 degree rise in minimum temperature can lead to an annual yield loss of 30% in Arabica in Tanzania. And another study showed that high precipitation and high temperature during the harvest can increase the risk of coffee bean defects for Robusta in Vietnam. And concerning the literature review of coffee studies, we see that most of statistical impact models often focusing on very specific locations in the world. For instance, here a study focused on only few municipalities in Brazil, or they have access to a very limited time series of the yields. So here another study used only 9 years of the yield data. And lastly, there's some study focused on the impact of climate change on coffee at local and global scales, but there's still room for improvements. And now move to the next point, the coffee yield simulations. So here we would like to study the impact of weather and impact on crop yield variability. And regarding the crop yield variability, of course, there are several factors can impact the yields, like the technology, biology, and the environments. But here we would like to focus on the weather and climate factors, as they has been proven to be very important to coffee and crop in general in many previous studies. So for instance, here is a study in Nature conclude that climate variation explains a third of global crop yield variabilities. And this example is statistical test with the weather information to explain the yield variability of global maize, rice, wheat, and soybeans. So again, in our case, we would like to focus on this weather and climate factors and aim at explaining those variations. And let's see which number we can obtain for coffee. And moving to the methodological approach, so here we use statistical and machine learning models. But in practice, there are two common approaches can be used, which are process-based or statistical models. So process-based models are based on mathematical and physical laws to simulate the plant function, and they're often done at a few scales. So to illustrate this, here is a simplified framework of wheat crop models. So this model takes the daily weather variables, the practice management, and genotypic parameters as the input, and then they try to simulate the water and nutrient movement inside the soil and in the atmosphere, and the processes occurring within the crop and in interaction with the environment. So this process-based model can be considered as a powerful tool, as they can provide a clear physiological mechanism to link the weather and the crop yield outcome. And then it's often done at a few scales, so it can be easy to calibrate and validate the models. However, due to this property, so large-scale implementations are not easy, and often recalibrations required when doing this type of models. And on the other hand, we have statistical models, which is based on data-driven approach to find the relations between the inputs or explanatory variables and the output, the yield, for instance. And this type of model is often applied at large scale, which is similar to the productive statistics of different administrative levels, for instance. And the advantage of this method is easy calculation, less time consuming, and it can be easier to apply to other locations. Also, a statistical model can account for various factors rather than the weather. However, by not including the plant physiological interaction, this model can be limited in the information that they can convey to the farmers. And statistical model often requires a long time recourse and can be misused easily. And I will illustrate this point in the following section of the presentations. So overall, we see that the two approaches have their own advantages and disadvantages. So here in this thesis, we will use statistical models as our tool to predict the weather-related factor for the crop variabilities. And from this title, the thesis have two main objectives. The first one is to develop statistical crop yield models using historical yield and weather data. And the second one is to study the impact of climate change on coffee productions using the future climate data. So in the first objective, we will aim to measure the sensitivity of crop to the weather conditions. And here we will develop two statistical applications, one traditional approach and one proposed tool to define the right model and assess its qualities. But due to the time limits, in the following, I will present only the second approaches. And then for the second objectives, so we did a review of calibration methods, or we can call this bias correction of climate model data. And I will then introduce some main approaches for this calibration method. And then a suitability model is developed to predict how suitable of the coffee production will change in the futures. So in the following, I will divide the talk into two main parts. The first, statistical crop yield model and climate change impact on coffee productions. And then I will conclude the study and give some perspective. So let's now move to the first part. So here I will introduce the materials, methodologies, and then the impact model, and finally the conclusions. So in this part, we will study an example of Vietnamese Robusta coffee. And as you can see here is a map of Vietnam. So Robusta coffee is mostly cultivated in the central highland areas. And among 12 major coffee producing districts, I will present a focus on Kumaras, which is located in the central of the study area and have a lot of coffees. So let me first give you an overview of coffee phenology. So it's a woody perennial evergreens, and it can be productive for 30 years, but it can be up to 80 years or more with good management. And then, unlike annual crops, coffee has a very complex 2-year phenological cycles. So here is an example showing the phenological stage for Robusta coffee in Vietnam. And we see that in 1 year, the coffee will be in vegetative state, and in the next year, it will be in productive state. So thus, the coffee will produce high yield in alternate years. But often in one coffee tree, there can be the overlap between the productive state and vegetative state. So it is very important to take into account the 2-year weather impacts when doing coffee studies. And then to build the model, we will use 2 databases. The first one is the weather data, in which we will use the airfile land data, and they aggregate the data with the resolution of 0.1 degrees. And then we average the data at the district scale. And finally, we will use the direct weather variables, which are derived directly from monthly precipitation and temperatures, as they are very important for the coffees. And the second database is the coffee data from General Statistics Office of Vietnam. And as you can see here is an example of the yield data for some district in Đắk Lắk. And we can see that from the yield data, there is the long-term change, which is often described by the change in practice and improved genetics. So which are the part that we're not interested in. So in the following, we'll remove this trend to have the yield anomaly values. And here, and now with our task is with the weather data, we will try to explain those variability in the yields. But we can see that here only 19 samples are available. And these limitations are our main constraint when doing statistical approach. However, we often have too many potential predictors that can include in the model because they are related to the crops, like the direct weather variable, like our case, but one can also consider the agroclimatic index because they can be better related to the crop than the direct variables. And this contradiction often leads to overfitting. So overfitting means that the model fits the training data set very well, but it cannot make good prediction on unseen data. So for instance, here is an example of a normal overfitting case where we want to perform a regression of the Y respect to the X. And here the overall database will be divided into 2, the training data set in blue, and we have the testing data set in orange. So we see that with a 5th order polynomials can fit very well the training data set, but is unable to perform on the testing data. And often we will aim at a good fit that balance between the 2 things. So it looks simple, but it can be problematic in crop modeling studies. And several approaches can be used to solve this problem, like regularization techniques that regularize the model parameters to constrain and discourage learning more complex model. Thus, it can avoid overfittings. And cross-validation can also be used as well, but this method can be misused easily. And also, we need to pay attention to statistical inference of the training data set and the unseen data. So often we can divide the overall database into 2 parts, the training data and the testing data. So in which the training can be used to fit the model parameters, but also to select the best model or here to test the performance. And then the testing data set is used to assess the model qualities. So it is valid if we are in the case of a data-rich situation, like many remote sensing studies. So here we often have the same behavior of the 2 data sets. We have the testing errors and the training error will decrease with model complexities. And dividing the overall database into 2 can be possible in case we have smaller database. And here cross-validation often used to have more training sample in iterations. So for instance, here I present the scheme of the leaf one now cross-validation method. And the idea is we will train our model n time with n is the number of samples. And in x time, we will use n minus 1 sample for training and leave 1 sample out for testing. And the overall score will be the average of n testing score, which is expected to be a robust assessment. However, so this is perfectly fine. However, if we are in the case, if we need to select among competing models, or we are in the case of a very limited database, it can pose problems. And using two data sets can lead to overfitting in model selections. Because in this case, the testing data will show different behavior than before. At some point, it can start to increase, implying the overfitting happens. And to solve these problems, we developed a method called live-throughout nested cross-validations. So by having a quite similar idea with the live-one-out method, but here, instead, in each time, instead of leaving 1 sample out, we will use n minus 2 sample for trainings and 1 sample for validation and another 1 sample for testing. So by doing that, we will have a data set for test the performance of the model or to select the best model, and then another independent data set to assess the model quality. So now with all the materials and tools in hand, we can move to the models, in which I will show an example of Robusta in Coursera. And here we will first perform several model selections by changing the number of potential predictors, number of inputs, and model types. So among different model types, we finally come up with the multilinear regression models, which I here for zero anomaly, beta is regression coefficients, and x is the input from direct weather variables. More sophisticated model will test, but actually in our coffee case, more is not better. This is like a bottleneck. Too complex model cannot fit our limited database problems. And then even with linear regression models, we can have different model selections. And then we will assess different models during the live-throughout approach, and a comparison with live-one-out will be performed as well. So here in this example, we will consider a linear regression with 5 input, and we will select our 5 input among different number of potential predictors from 5 to 38. So often we think that potential predictors are not involved in the model complexity, but this is very important choice in modeling. And the list of predictors that we might use can actually impact the models and the risk of overfittings. So here we also, in the y-axis, we have the root mean square error of different data sets, the training data, the testing, and can be the validation set as well. So in the case of live-one-out method, we see that the two data set, training and testing, show the same behavior. The errors decrease with the number of potential predictors. And it means that a model with more potential predictors will be the best here. But this can be not correct if we look at the live-throughout results. So we see that here again, we have the training error decrease with the number of potential predictors. So does the validation errors. But the testing errors start to increase when we increase the number of potential predictors. And in this case, live-throughout tell us that a simple model is the optimal one. And by having the same idea, we will perform different model selection by changing the number of input and model types. Same conclusion this meant. So live-one-out shows us that a more complex model is the best, but it can be misleading. But the live-throughout instead encourages us to choose simple models. Should be the optimal for our coffee case. And then the final model that we choose for the Robusta estimation using the live-throughout is the linear regression model with 3 inputs, precipitation and temperature, with the corresponding to the key moments of Robusta coffees. And these results are increment with the literature in the coffee phenology. So now by using these models from the live-throughout methods, let's look at the geo estimations. So we have here the geo anomaly data from 2000 until 2018. And we have in the solid line, the observation data, and then in dashed line as our estimations. So we see that our estimation is not perfect, but it was able to estimate some bad years with negative values and some good years as well. And overall, we have a correlation score between observation and estimation of about 0.6. And we can convert this correlation score into explained variance of 32.5%. And this result is in agreement with the study that I saw at the beginning for the global crop yields. And now, just for comparison purpose, so here I present also the results of this 2-hour method when we apply to an annual crops, which is a maize in one main department in France. So we have again here in black line, this is the observation data, and in gray lines, they are on the estimation within several months before the harvest. So we see that the maize is more weather sensitive than coffee by showing a good correlation score already 4 months before the harvest. And at the end of the season, we see that the weather information can explain about 45% of the yield data. And then, so in conclusion, we see that it's very challenging to identify an appropriate statistical model for coffee due to its complexity in terms of phenology, but also due to data limitations. But we was able to perform some statistical approach to estimate the weather impact on Robusta coffee. And with the live 2-hour method, we can able to calibrate, select, and assess competing models. Why using the live 1 hour alone can be misleading. And the precipitation and temperature during the development and fruit formations are very important for Robusta coffee. And the weather overall can explain up to 30% of the variation in coffee yield anomalies. So that was the first part about quantitative yield estimations. And now we will move to the second part, the climate change impact on coffee productions. So when climate change, the practice will change to adapt with these new environments. Or we can say there will be the feedback on the climate change. However, unfortunately, we will not have this type of information to include in our impact studies. And then, so just instead of a quantitative yield estimation, in the next part, we will go for a more qualitative task that try to estimate the suitability of the coffee in terms of the areas. But before going into the models, we will first look at the climate model data, which is really our major source of information for the future climate. However, this data often suffer from substantial bias, such as the structural or parametric uncertainties. So for instance, here we will see the map of the observations and the models of the mean temperature during the period of H1 until 2005. And if we look at the differences between the observation and the model, we can see that the model data are biased compared to the observations. And here is an example of systematic bias in terms of mean temperature, but actually many things can be different. So often we need to calibrate or bias correct this type of data before using them in the impact models. And here we define the term calibration as the method to transform the climate model simulation data towards more realistic values. And during the thesis, I have done a reviews on different methods to calibrate the climate model data, as you can see here in the table. But I'm not going into the detail, just to show that there are numerous calibration methods has been developed and used in impact models. And each method will aim to correct different properties. Like some method can correct the means, but some can correct the whole quantity of the climate data, or it can focus on the extremes. But the choice of a suitable method should be based on what is essential for the users. And then in the following, I will present briefly the idea of the main commonly used approach, which are the direct and the data approaches. So suppose that we have 3 data sets, which is the historical observation data and the model data during the historical and future periods. So now using 3 data sets, we want to obtain a calibrated data for the future period. So the direct approach will first estimate the differences in the statistical properties of the historical data, or we can call it a transfer function. And then this transfer function will be applied to the model data in the future to obtain the calibrated data. So that was for the direct approach. And then we have the dental approach, but this approach will first estimate the climate change signal, or actually it is the differences between the historical and future model data. And then this difference will be transferred into the observation data to obtain the calibrated ones. So apart from these two commonly used approaches, there are also recently there are quite a lot of quantile mapping methods that try to calibrate the climate model data, but also account for the model change signals. And we will call them as a combined approach. And in the following, we will use a combined approach to calibrate our regional climate data before being used in the impact models. And we choose this method because it shows a strong advantage in preserving the climate signals. So in conclusion, we will use a combined approach to calibrate our climate data to use it in the suitability models. And then in this model, we will focus on two areas, the Robusta in Vietnam and the Arabica in Brazil. So these two areas belong to the Southeast Asia and South America regions. So then to build the model, we will use two data sets. The first one is the climate data. So here for the observation, we will use again the aerophile line data, which will be integrated in the same scale as the model data. And for the model data, we will use the codex data for the Southeast Asia and South America regions. So in detail, we will use 8 models for Robusta and 6 models for Arabica. And they aggregate the data with the resolution of 0.22 degrees. And here we will study two scenarios, which is the low and high greenhouse gas emission, gas concentration scenarios, the RCP 2.6 and RCP 8.5. And then we will use monthly variables from precipitation, temperature, or evaporations to build a set of 12 environmental variables, which we use as our potential predictors for the suitability models. And this list of potential predictors has been selected using the literature reviews and expert recommendations. So then we have the second database, which is related to the coffee data. So same process will be done for Robusta and Arabicas, but let's first look at the Robusta in Vietnam. So we have here unlike the first part where we have the information about the yield. So in this part, we will use the database related to the location of the coffee farms. And this location data will be used from the coffee areas at the district level for Robusta in Vietnam. And the results of this location database will show in red point here, or what we call the present class, or the coffee samples. So the red dot is where it is suitable for the coffee. And now we want to document all the case that is when the coffee is absent or unsuitable, which is the process of finding the background points around the red dots in blue, where we know there is no coffee. And then with the two data sets, the coffee and background sample, we want to teach our model where it is suitable for coffee and where it is not. So similarly, we can have the database for Arabica in Brazil. And again, we will use the coffee areas at the municipality level to use this database. And finally, our suitability model can be built from two data sets, the weather data and the learning database. So in detail, with the weather data, we will perform a forward stepwise selection to have 3 important variables at our input. And then a neural network model will be used to, so we will first train the model on the learning database for current periods, and then we apply it to all the cells over the 2 study areas over different time periods for the current and 3 future periods. So it should be noted here is that the results of neural network is a continuous score from 0 to 1, and we will apply a threshold to determine if a cell is suitable or not for the coffee. So now let's look at the results for Robusta in Vietnam. So here we have the map showing the current and future suitabilities of the coffee under the high emission scenarios. So again, we have here the current, and the future suitability is the results of 8 regional climate model simulations. And here, then we will calculate the mean and the standard derivation for different time periods here. So we see that the largest suitable areas are in the mountainous locations, which is similar to the central highland of Vietnam. And then compared to the current suitability, so the highly suitable areas will decrease significantly in the futures. So for instance, here in 2060s, the area can be reduced by half compared to the current suitabilities. And we see that 8 regional climate models give quite similar results by showing a small standard derivation values for all 3 projected periods. And so that is the result for one scenario. So now we can actually look at the sensitivity to different scenarios. And here is the map showing the suitability change or the difference between future and current suitabilities that we have for 3 future periods under low and high emission scenarios. So here, dark magenta points mean that the point is suffer a drastic change from suitable to unsuitable, and dark green meaning that the point will suffer positive change. So we see that overall the climate impact are less pronounced in low emission scenarios than high emission scenarios. And then for the 2 scenarios, we see that most of study regions will become unsuitable by showing by a lot of magenta points. And overall, negative impacts become stronger towards the end of the centuries. So another factor that we can look at is the distribution of climate impacts. So here is the map showing the distribution of suitable Robusta areas by elevations. So we have in green the low emission scenario, and in red it is the high emission scenario. And in each period, I also plot the current distributions showing in black light. And we can see that the current coffee are most suitable in the area with the elevation from 200 to 900 meters. And this suitable area will decrease significantly in the futures for all 3 periods with an average loss of about 20% for the low emissions and 60% for the high emission scenarios. And the highest loss could be 80% in 2060s. And overall, we see that significant loss are found in low elevation areas, especially below 800 meters. And higher temperature are expected in the future could be one of the main reasons for this decrease in suitabilities. So that was for Robusta in Vietnam, and now similarly we can apply our suitable model for Arabica in Brazil. And here are the results. So again, we have the current and future suitabilities. So we see that high suitable areas will decrease significantly in the futures. And then we can also look at the suitability change. So again here for Arabica in Brazil, and we see that positive impact are found in southern part of the study areas, and overall negative impact becomes stronger towards the end of the centuries. And lastly, this is the distribution of climate impact by elevation. So again, we see that Arabica will be decreased significantly for the suitable areas in the future, and we will have an average loss of about 30% under low emission scenario and 50% under high emission scenarios. And similar to the Robusta case, we have significant loss are found in low elevation areas as well. So to conclude this part, we see that climate model data need to be calibrated before being used in the impact studies. And then the climate change has a negative impact on the 2 largest coffee growing areas of the world. We have an average loss of about 60% for Robusta and 50% for Arabicas under the high emission scenarios. And overall, significant loss are found in low elevation areas. And this suggests that mitigation strategy by shifting to higher elevation are possible, but the area will be fewer. So now let me conclude the study and we can look at some perspectives. But let me first just go back to the 2 objectives that I presented at the beginning. So to develop statistical crop-yield models and to study the impact of climate change. So throughout the presentation, we see that we need rigorous tools to select, validate, and assess our coffee models. And then whether information can account for up to 30% of Vietnamese Robusta geo anomalies. And when it comes to climate change impacts, we see that more negative impacts are expected on two largest coffee growing areas. So once again, we see that quantifying the impact of weather on crop is a task that we can do. But for coffee, it is challenging because due to its complex phenological cycle, but also due to the data limitations. And for other crops, it can be easier, and they are probably more weather sensitive than the coffee. So probably for the coffee, a suitability model is probably the way to go, that we can estimate the impact of climate change on the coffee suitable areas in the future. And then following this thesis, there's many perspectives can be done. So for instance, in terms of the meteorology, we can actually consider other predictors that are more related to crops, but of course, the addition of the predators should not come at the cost of overfeedings. And then we can use the mixed effect models or multi-crop models to compensate the lack of historical data. And also a combining approach between statical and process-based model can be possible as well. And based on what we have done and the tool already, we can extend our model to other crops. For instance, we can apply it to crop in France or in several European countries where we have quite a lot of yield data available. And then we can apply our model with a final temporal resolution and then apply it to different climate change impact assessments. Finally, we can develop an online platform to make a quick decision during the growing seasons or before and after the harvest. So that's it for my presentation, and thank you for your attention.